we talked about the layers of the atmosphere in the last class. And all right, so let's pick up from here. So the next thing that we are going to talk about is surface heating, like how the energy from the sun heats up our planet. Okay, so um, most of the radiation from the sun can penetrate the atmosphere. So we've seen that there are not all types of electromagnetic radiation can easily penetrate the atmosphere. Most of it is blocked by different gases in the atmosphere, but two types of electromagnetic radiation can penetrate the atmosphere, and they are visible light and some radio waves. So visible light and some radio waves can penetrate the atmosphere, but everything else, almost everything else, is blocked by the atmosphere. And that is why we are able to see the sun, because light from the sun, visible light from the sun, can get directly to the ground. Um, and also we discussed in chapter 5, we can place radio telescopes on the ground because radio waves can get all the way to the ground. But if you want to do astronomy with X-rays or gamma rays or infrared, then you have to place your telescope up in space because the atmosphere is going to block those electromagnetic waves. All right, so most of the solar radiation penetrates the atmosphere and gets to the ground, and it warms up the Earth's surface, right? So the Earth's surface absorbs all the light, all the energy coming from the sun. Most of it is in the form of visible light. So the Earth's atmosphere absorbs that. Then what happens? So after absorbing the energy from the sun, the Earth's surface re-radiates a lot of that energy. So we're absorbing energy from the sun, and then we're constantly re-radiating it uh, in the form of infrared radiation. So you might remember in chapter 4, we talked about how we are always giving off infrared radiation. Everything around us is giving off infrared radiation. So everything around us is constantly putting out infrared radiation. So we are receiving radiation from the sun in the form of visible light, and then we are giving off infrared radiation. All right. Now, a calculation was done by a very famous mathematician back in, I think, in the 1800s. And he calculated the following, that, okay, so if this is the Earth and it's receiving energy from the sun, right? And it's also giving out energy. So these outward directed arrows are the energy that's given out in the form of infrared radiation. So if we are constantly receiving energy and giving off energy, then how much energy are we keeping, right? So you can calculate that. I mean, this person did this calculation that if this is the rate at which we are receiving energy, this is the rate at which we are putting out energy. So how much, I mean, if we are putting out all the energy that we are receiving, then what should our temperature be, right? So if we're receiving energy at a certain rate and also putting out energy at that same rate, meaning that we are not keeping any of that energy, then what should the temperature of the Earth be? And what he found out, to his amazement, was that the temperature of the Earth should be something like minus 18 degrees Celsius or minus 25 degrees Fahrenheit. So that means if we were radiating all the energy that we are receiving from the sun, then the temperature of the Earth would be extremely, extremely, extremely cold, right? If all the energy that is coming in from the sun were allowed to leave. So what that tells us is that we are clearly not uh, letting all the energy go. We are clearly holding on to some of that energy, right? And so that is why we have a nice, warm, moderate temperature on our planet. Because if we were not able to do that, if we were not able to hold on to some of that energy we are receiving from the sun, if we just radiated it all away, then the planet would be extremely, extremely cold. At minus 18 degrees Celsius, all the oceans of the planet would be frozen solid. So there would not be any trace of liquid water on our planet. All the oceans would be completely frozen solid. All oceans, lakes, rivers, all bodies of water would be completely frozen solid. So we're clearly trapping some of that energy in the atmosphere and not letting it escape. Is everybody clear about that? So the question is, how is the Earth's atmosphere trapping energy? And so that's what we're going to talk about next. Okay, so the way we trap energy is or yeah. So the way we trap energy in the atmosphere. So the question is, how does the Earth's atmosphere trap energy or heat? So the way the Earth's atmosphere traps energy is as follows. In the atmosphere, there is a type of a particular gas called carbon dioxide. Does anybody remember what the atmosphere is made up of? So the Earth's atmosphere, what's the most predominant constituent of the Earth's atmosphere? Which gas?
The nitrogen?
Yes, nitrogen. That is, and since we are reviewing, we might as well just go over that. Nitrogen is what percent?
78%.
78%. And what's the next one?
Oxygen?
Oxygen, exactly. And what percent is that?
21%.
21%. So together they make up 99% of the Earth's atmosphere. And then the remaining 1%, most of it is argon. So argon is 0.9% or something like that. And then you have very trace amounts of things like carbon dioxide and water vapor, methane. So you have very small trace amounts of these gases in the atmosphere. Now, carbon dioxide is the most important for the purpose of trapping heat. So how does carbon dioxide trap heat? The way carbon dioxide traps heat is as follows. So here's a carbon dioxide molecule. I'll just draw the chemical symbol of carbon dioxide, which is drawn like this. So that you've got two O's and a C in the middle, and the equal two looking things are like the sticks which hold them together. So this is a carbon dioxide molecule. So suppose you have, so this is the ground, right? Here is the sun. The sun is giving off visible light. So I'm going to indicate that with these yellow arrows. So this is visible light coming in from the sun. And the earth is radiating that energy back as infrared. So these red arrows are basically the infrared radiation going out from the earth, not just the ground, but from anything on the earth: trees, houses, buildings, people, dogs, cats, birds, everything is giving off infrared radiation. And we just discussed that if all this infrared radiation could just simply escape, then we would be in very big trouble, because the earth would be extremely, extremely cold if all this infrared radiation could escape. So how does the infrared radiation not escape? What prevents it from escaping? It is this little humble little carbon dioxide molecule. So when infrared radiation hits this carbon dioxide molecule, or you can also think of the infrared radiation as these infrared photons. You know what photons are? They're particles of light. When these infrared photons hit the carbon dioxide molecule, the carbon dioxide molecule eats them up. So it takes the energy of that infrared photon and immediately radiates it out in every direction. So the infrared radiation hits the carbon dioxide molecule, the carbon dioxide eats it up, and then spreads it out in every direction. So you can see that the carbon dioxide makes it difficult for this infrared radiation to escape, because every time it hits a carbon dioxide molecule, it gets absorbed and then spread out in all directions. Some of it is sent back to the earth, some of it is sent sideways, some of it is sent, some of it keeps going outwards. So the carbon dioxide molecules trap the heat, uh, the infrared radiation as it's trying to escape, and keep it trapped inside the Earth's atmosphere. So this role uh, played by the carbon dioxide molecule is very important. And it is what traps heat in the atmosphere. And as a result of this, the carbon dioxide gas has a name. What do we call the gases which trap heat? There's a very famous name for these kinds of gases that trap heat. Does anybody know what they're called? They're called greenhouse gases. And carbon dioxide are called greenhouse gases. And carbon dioxide is the most important greenhouse gas. it does the best job of trapping heat. So hopefully it's clear how the carbon dioxide is trapping the heat. As the infrared radiation hits the carbon dioxide molecule, it's absorbed and it's re-radiated in every direction. And so it makes it hard for the infrared radiation to escape. It just stops it. Okay, Kaylee had a question, go ahead.
Are greenhouse gases bad?
No, no, they're not bad at
Because
all. In fact,
I've
they play,
heard that
yeah.
some of them, like, I don't know, I've heard that they were bad, so I was not
I'll tell
sure.
you, I'll tell you why they're bad in just a little bit. But by themselves, and they're bad not for their fault, it's because of our fault. And I'm going to explain that in just a little bit. But the very important role that greenhouse gases play is to trap the heat. If we did not have greenhouse gases, if we did not have carbon dioxide in our atmosphere, then the Earth would not be livable at all. The Earth would be completely frozen. Rena, what question did you have?
Could you move your screen back down so I can see what question you asked at the beginning? Like,
Oh,
yeah,
what
move it
question?
down.
Oh, yeah. So
Yeah, that's
yeah,
correct.
how does the Earth's atmosphere trap heat? So what we just discussed is that the presence of certain greenhouse gases like carbon dioxide uh, makes it difficult for the heat to escape. So hopefully that part is clear to all of you, how it's difficult for the heat to escape, because these greenhouse gas molecules will trap the heat and will absorb that heat and spread it out in all directions. So some of it does manage to escape, but a lot of it is just sent back, right, down back towards the Earth. And so that is how the greenhouse gases prevent the heat from escaping. Now, carbon dioxide is the most important greenhouse gas, but there are some other greenhouse gases as well. And here are some examples. Um, Other greenhouse gases are, oops. So other greenhouse gases are water vapor, which is just H2O. That's just water in gas form. Um, Another one is methane. Methane. Do any of you know the chemical formula for methane? Probably not. It's CH4. So it consists of one carbon atom and 4 hydrogen atoms. It's CH4 is the chemical formula for methane. You don't need to know chemical formulas for this course. Water, I'm sure you know, it's H2O because it consists of 2 hydrogen atoms and 1 oxygen atom. That's the water molecule. So water vapor, methane, and carbon dioxide are greenhouse gases, but the most important greenhouse gas is carbon dioxide. Right? Okay, so carbon dioxide and other greenhouse gases play this absolutely crucial role of trapping heat. So greenhouse gases trap heat in the atmosphere. So that is the most important role that they play, and hopefully it's clear to you how they play that role. Okay, so that's what I have in my slide here. The trace amounts of water vapor and carbon dioxide. Water vapor is of course H2O. And carbon dioxide trap a large part of the energy uh, that's coming in from the sun in the atmosphere, right? Okay, and so this maintains warmth on our planet and keeps our oceans liquid. So without this heat being trapped in the atmosphere, there's no way the oceans would have been liquid water. They would have been frozen solid. All right. So that is the role played by greenhouse gases. They trap heat in our atmosphere. What has been happening since the Industrial Revolution is that we have been pumping an enormous amount of carbon dioxide in the atmosphere. How have we been pumping carbon dioxide in the atmosphere? Because so we use fossil fuels, right? So fossil fuels are basically coal and oil, right? So the way we use coal and oil is that we basically in a coal plant you burn coal, so that produces a lot of heat, and that heat is used to drive steam turbines and stuff like that. And so you can so you're using heat as a form of energy. You're unlocking the energy inside the coal by burning it, and that releases heat, and then you're using that heat energy for other things like driving turbines and stuff like that. Um, so oil does the same thing. So oil has energy trapped inside it, and then when you when you drive your car, you're burning that oil basically and creating these little explosions, and those little explosions are what drive the axle of your car and make your car move. So in both the processes, you're burning these fuels in order to generate energy. Whenever you burn something, you produce carbon dioxide. And so all of these processes release carbon dioxide in the atmosphere. So what we've been doing for the last 150 years or so, ever since the Industrial Revolution, 150, 200 years, is we have been steadily pumping carbon dioxide into the atmosphere, right? What do you think would be the effect of putting in more carbon dioxide, more greenhouse gases in the atmosphere? What do you think the effect would be? You can see the role played by greenhouse gases written on the board here. So what would be the effect of putting more greenhouse gases in the atmosphere?
Well, because it traps heat, it would just make everything so hot, and that's why global warming is
Yes,
something like
so
iceberg.
exactly. So if you put in more carbon dioxide in the atmosphere, it's going to trap more heat because that's its job. If you put in more carbon dioxide in the atmosphere, it's just going to it's going to trap more heat. And so the heat, so it will be even more difficult for the heat to escape. And so the heat will be trapped in our atmosphere. And so we are going to have, that's going to make the whole planet really hot. It's going to raise the temperature of the average temperature of the planet, right? And that has many, many bad, very, very bad consequences, increasing the average temperature of the planet, right? Yeah, Kelly, what question did you have?
This is just like a quick question, but like
Sure.
what kind of things could we do, like just personally in our own day-to-day lives, could we do to like help reduce that?
Yeah, unfortunately, there is not much that we can do at this point. I mean, we have unfortunately almost reached a point of no return. So individually, we can just try to use less fossil fuels, like not drive that much. But when we are using you can't tell people these days not to use electricity. So electricity is absolutely essential, or heat. I mean, if you live in a cold place, you have to
Yeah.
use heat. But so maybe you can just drive less. But this problem has gone to a level where there is not much that any individual person can do. I mean, this has to be something that governments have to enforce. That governments have to say that, okay, we are cutting down, we are going to shut down all these coal plants, which produce enormous amounts of carbon dioxide. So shutting down a large number of coal plants, not just in one country, but in all over the world, and trying to find energy from alternative sources would be the only solution. But unfortunately, we have really gone to a stage which is very, very bad. So unless over the next 100 years or so, our governments of the world get their acts together, it's just not going to happen. I mean,
Are
we
there
are
any
really,
like
yeah.
petitions or something that we can sign to like help
Yeah,
shut things down,
I'm
or
not sure about that right now, but there was the Paris Climate Accord, which was which was an effort that was made a couple of years ago for countries to come together and sort of uniformly enforce more and more regulations. But you know the history with that. Our previous president decided that's not a good idea. Our current president decided to again go back to the Paris Climate Accord. But something like that has to be done at the governmental level all over the world, and people really need to see this, take this very seriously, and not
yeah,
politicize this issue, because this is not a political issue at all. It's a scientific issue. Like it's backed by actual scientific data. And
yeah,
so I mean, like that, I've got two bullet points over here. um, these two are absolute hard facts. Like there is no arguing with these. So one of them is that the amount of carbon dioxide in our planet has been steadily increasing. This is not somebody's interpretation. It's actually measured data. The amount of carbon dioxide has been increasing. The data is out there. Like there is no arguing with that. And another thing that we know for sure, and you would probably expect it now that you understand the science, the global temperatures have also been rising. So these two facts are completely established. The amount of carbon dioxide has been increasing over, not just over the last 150 years, but I mean, it's been increasing drastically over the last 150 years. And also the amount of temperature, I mean, the temperature of the Earth has been also been increasing. Now, you might say that how do we know that the temperature of the amount of carbon dioxide has been increasing over the last 150 years? this was actually, I'll just, since you guys asked some questions, I'll just talk a little more about this. So the whole thing of the amount of carbon dioxide increasing was first noticed sometime, I think in 1956 or 1958, when a young scientist at Caltech, a very famous university, decided to do an experiment and measure the amount of carbon dioxide in the air. So he had this really sophisticated piece of equipment which can measure carbon dioxide in the air. He took it to Mauna Loa in Hawaii, because that's a desert area. It's a great place to measure the carbon dioxide in the air. And he measured the carbon dioxide in the air, and he found that he measured it twice. He measured it during the summer and also during the winter. And he found that there is less carbon dioxide in the air during the winter and more carbon dioxide during the summer. Can you guess why?
Because it's colder in the winter?
Not
know.
quite the reason. So plants breathe in carbon dioxide and breathe out oxygen, right? So in the winter, what happens is that a lot of plants don't have leaves during the winter, and so there is less carbon dioxide is breathed in by the plants. So you've got more carbon dioxide in the atmosphere during the winter, less during the summer, and so he was intrigued by that, and he said that, wow, this almost is like the Earth, our planet breathing, like it's breathing out, breathing in. He put it in poetic terms. But his equipment was so great that other scientists decided that, hey, why don't we do this measurement every year? So they measured very accurately measured the amount of carbon dioxide every year since 1958. And the graph that they have goes up like this. So every year, the amount of carbon dioxide is drastically going up. And actually, I'll just show you that graph right now. The actual graph, just 1 second, let me just find it. 1958. Okay, yeah, here it is. So this is the measurement that I just talked about. The carbon dioxide is measured in parts per million. So in 1958, when our young scientists did this experiment for the first time, it was something like 315 parts per million. And in 2021, it's gone up to 420 parts per million. So it's gone up by a drastic amount in the last 1960 to 220. So the last 60 years, you can see how drastically it's gone up. And you can see this sawtooth up and down. It's because of the breathing of our planet. Like it's more carbon dioxide in the summer, less in the winter, and so on. So you can see this sawtooth up and down. But you can see that the amount of carbon dioxide has gone up. And this is actual hard data. Now, you might say that, okay, so the carbon dioxide was first formally measured in 1958 by this young scientist. How do we know that this doesn't just happen all the time? Like maybe the amount of carbon dioxide on our planet just goes up and goes down and goes up and goes down, and we are just seeing an upswing from 1958 to 1960. How do we know that this is something that's happening because of us and it did not happen in the past? That's a very good question. There is a very good answer to that as well. We have a way of independently measuring what the amount of carbon dioxide was in our atmosphere up to millions of years ago. And do any of you know how we could do that? Like, how can we possibly figure out how much carbon dioxide there was in the atmosphere millions of years ago?
Can you do it with like the way that they do rocks and stuff and see all the different like levels of stuff
Yes.
built
So
up?
the way, yes, absolutely correct thinking. The way they do it is by ice coring. So there are these in Antarctica, you have these huge, very, very, very thick glaciers, and so there the ice has been accumulating for literally millions of years. So you have this very, very thick slab of ice, which has been growing for millions of years. So if you sort of if you code into that, so if you sort of send a tube down through the ice and then collect a sample of the ice, so the oldest ice will be over here and the youngest ice will be over here. So at the bottom of your sample, so basically what they do is they have these huge tubes which they force into the ice. They force the whole tube into the ice and then seal off the bottom and bring the tube out. So they have this whole column of ice. So with the bottom of the column being the oldest ice and the top of the column being the youngest ice. So the way the ice formed was it snowed at some point, right? And snow has a lot of air trapped in it, right? And so when the snow freezes, those the air inside the snow gets trapped as bubbles. And so you have bubbles of air inside that ice. You have bubbles of air that are millions of years old. So scientists have ways of very, very carefully analyzing the different bubbles of air. So I'll draw a few bubbles here and there. So you have air trapped in little tiny bubbles of air, which are trapped inside the ice. And so scientists can very, very carefully study those bubbles of air and see what are the gases present inside those bubbles of air, right? And so they can clearly see how much carbon dioxide there was inside that bubble of air, right? And so they can see that the amount of carbon dioxide in the atmosphere over millions of years does fluctuate, but not as drastically as it is fluctuating now. And it never has gone up so high continuously. That has never happened in the past before, right? And so this is clearly something that we are doing. And not only that, scientists, by looking at what kind of gases there are in these little bubbles of air, suppose they find this one bubble, which is from 10 million years ago, they'll know exactly what kind of gases were there in the atmosphere 10 million years ago, because that's what's inside that little bubble of air trapped in the ice. And by knowing how much these gases trap heat and stuff like that, they can figure out what the temperature was 10 million years ago. And so it is possible for us to not only figure out how much carbon dioxide there was in the atmosphere up to millions of years ago, we can also figure out what the temperature of the Earth was up to millions of years ago. And what we find is what I just said, that the carbon dioxide has been recently, it's been increasing steadily at an alarming rate, and the temperature has also been increasing. So, and the reason for that is absolutely clear. It's because carbon dioxide is a very effective greenhouse gas, and we've been pumping more and more and more of that into the atmosphere. And so that has had the completely expected effect. It has been raising the temperature of our planet. So this is called climate change and global warming. And so it is a serious concern right now. Of course, we have a much more serious concern with the coronavirus at the moment. So people are not thinking of it now, but it was a pretty serious concern, and it will continue to be a very serious concern as we go forward. Okay. So what are the consequences of global warming? There are many, many consequences of global warming. One of them is that, and we can already see these consequences. Like maybe 10 years ago, people used to say that, oh, this is all just fantasy and scaremongering and all that. We don't really need to worry about this. But the things that people were warning about 10 years ago are happening all over the world right now. So when the temperature of the planet increases, a lot of bad things happen. One of them is that the ice in the Antarctic region, so that we have huge amounts of ice trapped in the poles, the North Pole and the South Pole, the ice starts melting, right? And so where does that melted ice go? It goes into the ocean. And so you have a lot of extra water in the oceans. And when you have extra water in the oceans, what happens is that the level of the ocean is going to rise up, right? Because the water has to, if you just pump more water into the ocean, it's just going to overflow, right? So the level of the ocean level will go up. And as a result of that, many places which are coastal regions, which are habitable now, will no longer be habitable later on. And this can be seen already happening in many places. There are many small islands in the Pacific where people are extremely worried that the island is not going to last for another 20 years or so. So they have to just abandon their homes and everything and just find a different place to live, because they can see clearly how the sea level is rising, and it's pretty obvious that the island is not going to be around for more than another 20 years or so. There are islands even close in North Carolina, like there are some islands in North Carolina where the sea level has gone up tremendously, and people are really concerned that that it might not last for very long. Those places might not be habitable for very long. As the sea level goes up drastically, many coastal regions of the US might go under the ocean. Maybe if things continue, maybe another 100, 200 years later, Nashville might be a coastal city. So people might, like downtown Nashville might be by the ocean. So that is really, really scary. The other thing is that when you have too much energy or heat available, so that energy can be utilized by storms, right? So storms ultimately have to get energy from somewhere. And so when you have a lot of energy available and it's trapped in the atmosphere by all our carbon dioxide, you will get much more scarier and much more powerful storms, tornadoes and hurricanes, and more of them. And there is a general trend over the last few years. We have been finding that there have been more and more storms, and the storms have been much more stronger than on average. So this is a trend that will continue as more and more heat is trapped, because this energy is available. So storms, it's going to go into making bigger storms and more frequent storms and more powerful storms. So that is another consequence. There are many scary consequences, like many ecosystems, fragile ecosystems might be destroyed as a result of the global climate change. So it's definitely something that needs to be taken seriously, not just at an individual level, but governments need to take this seriously and do whatever they can to stop pumping carbon dioxide into the atmosphere. All right. So we talked about that. Okay, so the next thing that we're going to talk about is the origin of the Earth's atmosphere. So we have a very unique atmosphere. When we study other planets like Venus and Mars, we will find that their atmospheres are very different than ours. Our atmosphere is very unique. There is no other planet in the solar system that has an atmosphere like us. And so why is the Earth's atmosphere the way it is? And what is the history of the Earth's atmosphere? So that's what we're going to very briefly talk about now. So it's believed, so we talked in chapter 6, we talked about how the Earth was formed, like how all the other planets were formed. So it started out as these little rocks. So at first you had the primordial nebula, and then the dust grains inside the primordial nebula started acting as condensation sites. And so more and more gases started to condense out on those dust grains and forming these rocks, which kept growing and started, and they became the planetesimals. And eventually the planetesimals turned into the planets. So we talked about all this earlier. So in the very early history of the solar system, the Earth was constantly being bombarded by other objects. So the solar system was very violent place at that time. So there was constant collisions going on between different things, and the Earth was constantly being bombarded from every direction by asteroids of all sizes. So the very early history of the solar system, if the Earth had any atmosphere at all, it would have most likely been made up of gases like hydrogen, helium, methane, ammonia, water vapor, because these were the gases that were common in the very early solar system, right? And this atmosphere, this would be called the primary atmosphere of the Earth, the very first atmosphere that it had. It would not have lasted for very long. So within half a billion years of the Earth formation, these gases would have just escaped the Earth. So they would have just flown off. Because these are all light gases, right? So the atmosphere that we have now is believed to be the secondary atmosphere of the Earth. So it's an atmosphere that formed much later as a result of outgassing. So what is outgassing? Outgassing means the gases that are released during volcanic activities. So it's believed that much later on, there was a lot of volcanic activity on the Earth, and volcanic activity releases gases, right? So the volcanic gases formed the atmosphere of the Earth that we see right now. Now, volcanic gases, what kind of gases do you have that come out of volcanic activity? So they are rich in water vapor, methane, carbon dioxide and sulfur dioxide. and also nitrogen. So I forgot to put that over here, nitrogen. I have that in the latest version of the slide. It's not showing up over here. Okay, and also other compounds that contain nitrogen. So ammonia, nitric oxide, these are all compounds that contain nitrogen. So let's just write these down. So the secondary atmosphere, so the Earth's atmosphere started from the secondary atmosphere of our planet. The primary atmosphere would just fly off into space. The secondary atmosphere has water vapor, carbon dioxide, sulfur dioxide, SO2 is sulfur dioxide, nitrogen, the symbol for nitrogen is N2. And then you have molecules which have nitrogen, like ammonia, NH3 is ammonia. That's a gas that has nitrogen and hydrogen. Ammonium hydrosulfide. Yeah, I didn't put that. Nitric oxide is another nitrogen containing gas. Nitric oxide. So these are the gases that were there in the in the first atmosphere that the Earth really had, the Earth's first real atmosphere. Now, that's not what our atmosphere has at all, right? Our atmosphere looks very different from this. So how did this early atmosphere of the Earth turn into the atmosphere that we have now? The atmosphere that we have now is mostly nitrogen and oxygen. That's what we have in the atmosphere right now. We don't have any of this stuff in our atmosphere. We do have a little bit of carbon dioxide, but this looks very different from the atmosphere that we have now. So how did this turn into the atmosphere we have now? That's what I'm going to discuss now. So the sun is constantly putting out ultraviolet radiation. So the sun mostly produces visible light and infrared, but it also produces a significant amount of ultraviolet radiation. So ultraviolet radiation is very energetic radiation. And so it's quite powerful radiation, right? Because it's got a shorter wavelength, as we've discussed in chapter 3. So it has a shorter wavelength, much shorter wavelength than visible light. And so it gives off, it's much more, it carries a lot more energy. So the ultraviolet radiation, what it does is that when it hits a molecule, so suppose you've got a water molecule is H2O. So here you've got 2 hydrogen atoms and 1 oxygen atom. So if an ultraviolet molecule, ultraviolet radiation photon comes and hits this water molecule, what it's going to do is that it's just going to snap it into, it's just going to break it up. So it might just snap off 1 hydrogen, right? And just leave the 1 hydrogen loose, and the oxygen and the hydrogen flow by itself. So it might just break off this 1 hydrogen. So ultraviolet radiation is really bad for molecules. It's like firing, it's like these molecules are these Lego structures, right? And just imagine that the ultraviolet photon is like you're shooting a Lego structure with a BB gun. As soon as the pellet hits the Lego structure, it's just going to break it up and the pieces will start flying off in different directions. So that's what the ultraviolet radiation does to molecules in the atmosphere, right? So all of these molecules were constantly bombarded by ultraviolet radiation coming from the sun, and that would break the water molecules, that would break the carbon dioxide molecules, sulfur dioxide, ammonia, nitric oxide, everything would just be broken up, right? Now, whatever has hydrogen in it, like this has some hydrogen in it, the water vapor has some hydrogen in it. As soon as the hydrogen is broken from the molecule, hydrogen is a very light gas, so it will immediately escape. So it's very difficult to hold on to hydrogen because it's a very light gas. So the ultraviolet radiation from the sun would hit everything that has hydrogen in it and liberate the hydrogen, which would immediately fly away, right? What about carbon dioxide and let's talk about carbon dioxide and water vapor. So once the temperature of the Earth went down a little bit, so at first the Earth was very, very hot, which is when all these gases were released. But when the Earth got cooler, the carbon dioxide, so the water vapor started condensing. So you know that steam, when it gets cooler, it turns into droplets of water. So the water vapor in the Earth's atmosphere started turning into droplets of water, which started raining down, and all that water vapor that was in the atmosphere turned into the waters of the ocean. It's hard to imagine rain filling up the ocean, but that's what happened. So as the Earth started cooling, uh, all the water vapor that was in the atmosphere turned into liquid water and filled up the oceans, right? And so once the liquid water, once we had oceans, uh, carbon dioxide dissolves very well in water. So carbon dioxide can easily dissolve in water. So the carbon dioxide started dissolving in the water of the oceans, and it just dissolved in there. And so the carbon dioxide went away from the atmosphere. So water vapor and carbon dioxide were gone because water vapor turned into liquid water, and carbon dioxide, most of the carbon dioxide dissolved in that liquid water and got and so it went into the oceans, right? So those two are gone from the atmosphere. And also the sulfur dioxide is also absorbed by also dissolves in water, so that also went away. So now you're left with nitrogen, right? And you're left with these guys, ammonia and nitric oxide. So once these were hit by the UV, they were just broken up. So anything that has hydrogen, once it's broken up, the hydrogen just flies away. So you can see that you're just left with a lot of nitrogen, right? So you have a very nitrogen-rich atmosphere. And so that is why so much of our atmosphere is made up of nitrogen, right? What about this little oxygen over here? Once this oxygen is liberated from this nitric oxide molecule, oxygen is actually a very highly reactive gas. So it will immediately react with something and get absorbed into that. So you won't have oxygen floating around in the atmosphere, right? So one thing we have understood is why our atmosphere has so much nitrogen. That makes sense? So please make sure that the sequence of events is clear. I told you how sunlight can break molecules, right? So we talked about that. Okay, then we talked about how you have so much water vapor and carbon dioxide in the atmosphere. So once the temperature cooled a little bit, the water vapor turned into the water of the oceans, right? And so once you have oceans of water, liquid water, that will immediately absorb carbon dioxide out of the atmosphere because carbon dioxide dissolves very well in water. So the carbon dioxide and the sulfur dioxide will dissolve into the water, and that will take a lot of it out of the atmosphere. So that's why we don't see any water or any carbon dioxide or sulfur dioxide in our atmosphere, because long time ago they went into the oceans. And so that leaves nitrogen gas, and it also leaves compounds containing nitrogen like ammonia, nitric oxide. And so when these compounds were bombarded by the ultraviolet radiation, they got broken up, and the hydrogen, anything that had hydrogen, that hydrogen just flew off into space, and you're just left with nitrogen. And so you can see that as a result of this process, the atmosphere would be mostly nitrogen, right? So that explains why our atmosphere has so much nitrogen. We see that our atmosphere is 78% nitrogen. And so this explains why our atmosphere has so much nitrogen. Everything else was either taken out of the atmosphere or flew off into space. And so that's why we are just left with the nitrogen. The next question is, why do we have so much oxygen, right? So 28% of our, 21% of our atmosphere is oxygen. Why do we have so much oxygen in our atmosphere? Does anybody know where all the oxygen came from? The place where the oxygen came from, or the region, so this is what we just talked about. As the Earth's temperature fell, water vapor condensed to form oceans. The carbon dioxide and the sulfur dioxide dissolved in the oceans or combined with surface rocks. Any free oxygen that was in the atmosphere would have just reacted with something, and would have just been quickly removed from the atmosphere. Oxygen, as I told you, is a very reactive gas. So you can't have a lot of unless oxygen is constantly being replenished. If you have a certain amount of oxygen to start with, after a while it'll be gone because it's constantly reacting with stuff. So when you cut fruits, fresh fruits, and if you leave them out for a while, you see that there's a sort of discoloration of the fruits, and that is because they're combining with oxygen. Iron, if it's left out in the open, rusts. So that is iron oxide. That rust, that red powder is iron oxide. That's the result of iron combining with oxygen. Many rocks will also combine with oxygen and get this reddish coloration. And so oxygen always reacts with things. So unless there is a supply of constant replenishing of the oxygen, it will not last in the atmosphere for very long. So so the question is, why does our atmosphere have so much oxygen? The answer is life. So life appeared first in our oceans about 3.5 billion years ago. So that is when life appeared in our oceans. And the very first organisms began to produce oxygen. So we discussed how plants take in carbon dioxide, breathe in carbon dioxide and breathe out oxygen. They don't really breathe, but they take in carbon dioxide and release oxygen. And so the very first life forms which appeared in the oceans started producing oxygen. And so once you have, and you know that life propagates, right? So once you have some life, it propagates, and you have more and more and more life forms of different kinds. And they were all plant life forms. So they started producing oxygen. They started taking out carbon dioxide and producing oxygen. And so as a result of that, we had a supply of oxygen in the atmosphere, right? It was these early plants. And so as you had more and more, as life started proliferating in the oceans and then eventually onto land, you had this powerhouse which was constantly producing oxygen, taking in carbon dioxide, producing oxygen. And then once you had a significant amount of oxygen in the atmosphere, what started happening was that ozone started forming. So we talked about ozone in the last class. Can somebody remind me, what does ozone do again, and where do we find it? Or what's the deal with ozone? We talked about that in the last class. Anybody remember? No one remembers? Okay, so ozone is basically made of 3 oxygen atoms instead of 2. So oxygen gas consists of 2 oxygen atoms, but ozone, so these circles are O's for oxygen atoms. So this is oxygen gas that you breathe in, and this is ozone gas. So ozone is present in our stratosphere. So that's about 25 miles above the surface of the Earth. In the stratosphere, you've got a layer of ozone. And what that does is that ozone absorbs ultraviolet radiation from the sun. So ozone protects us from ultraviolet radiation. So once we had a significant amount of oxygen in the atmosphere, some of that converted into ozone. And the ozone started accumulating in the stratosphere of our planet, and it started absorbing the ultraviolet radiation coming in from the sun. And so that provided us, provided an umbrella, or that provided protection to the life forms on the Earth, because the earliest life forms would not have survived the ultraviolet radiation from the sun, because it would have just killed them off if the ultraviolet radiation could have come to the Earth. But once you had this ozone in the atmosphere, it started blocking the ultraviolet radiation, and it made it easier for life to proliferate on the Earth, right? And so you had more and more life forms developing on the Earth, which were producing more and more oxygen. And as a result of that, you have an enormous supply of oxygen on our planet. Yeah, Kaylee, what question did you have?
I heard like a long time ago about a hole in the ozone. Is that true or is that false?
Yeah, that's true. So I talked about that, in fact, in the last lecture. So when you see the recording, So when you see the recording, I talked about that in the last lecture. It's also there in the earlier part of this chapter. So it's definitely true. So that was a climate crisis in the last decade or so. But governments of the world were able to get their act together and take serious measures and stop that from becoming a major problem. And so we were able to get our act together just at the right moment and stop producing those harmful chemicals which were damaging the ozone layer in the atmosphere. But we don't know whether we can do the same thing again this generation. So
Yeah.
okay, with the climate change. All right.
Thank you. Sorry.
Yeah. So we talked about yeah. So that is how. Um, yeah, so life appeared in the oceans about 3.5 billion years ago. The first organisms began to produce atmospheric oxygen because they were all plant life forms, and plant life forms take in carbon dioxide, give out oxygen. So the ozone layer formed for the first time, and that shielded the surface of the Earth from harmful ultraviolet radiation. So by harmful radiation, I mean UV radiation. And then once we had the ozone layer, that made it that made it much easier for life to survive on the planet, because as I said, the UV radiation coming straight down would have just killed off all the earlier life forms. So without the ozone layer, life would not have been very possible on our planet. But once the ozone layer was formed, it was easier for life to spread to the land and flourish, right? So that is why we have so much oxygen in our atmosphere. It is the result of life uh, appearing in our planet for the first time 3.5 billion years ago. Scientists still don't understand how life was created. Like what exactly caused the first life forms to happen is not very well understood. But yeah, okay. All right, so we're going to take a break now. But before we do that, I'll just leave you with one thought, which is really, really amazing thing. So when you look at a plant or a tree, okay, so when you look at a tree, for example, most of us think that it's something that just came out of the ground. It's an extension of the earth, right? That's what you think when you see a tree. It came out of the ground, some extension of the earth. But that's not what it is at all. A tree is basically sunshine solidified, sunshine and water solidified. A tree is basically a solidified, sunshine and air. That is what a tree is. A tree is solidified sunshine and air. You might find that really hard to believe, but let me explain that. So what is a tree? What is a tree made up of? So trees, or most life forms, are made up of carbon, right? So the body of a tree, the trunks, branches, leaves, everything is made up of these long molecules of carbon, which are mostly carbon. So these long chains of carbon atoms is what makes up the tree. Where did this carbon come from? Can you guess where this carbon came from? This carbon came from the carbon dioxide in the atmosphere, the carbon dioxide gas in the atmosphere. So basically what the tree does all the time, particularly the leaves of the tree do all the time, is that they take carbon dioxide from the atmosphere and they use the energy of the sun, the energy of visible light from the sun, to carry out a process, a biological process called photosynthesis, which you might have heard of in your science classes in school. So what photosynthesis is that carbon dioxide of the atmosphere is broken up with the help of the energy of the sunlight, and that carbon from the carbon dioxide is added to the plant's body, right? And what about the oxygen? It goes out into the atmosphere. So that is how plants take in carbon from carbon dioxide and add it to their body, and that's how the plant grows and releases the oxygen into the atmosphere. So you can see that a tree is basically just solidified sunshine and air and carbon dioxide in the air. And sunshine is necessary to break up that carbon dioxide and separate the carbon from the carbon dioxide molecule and in order to grow the body of the tree. What does the ground contribute to the tree? So part of this process of photosynthesis, you also need water, and so that water comes from the earth. So or you have to so that water comes from the roots of the tree. So the earth plays the role of supplying the water and some nutrients, but essentially the majority of the tree is basically solidified sunshine and air. So when you look at trees from now on, just think of them as solidified sunshine and air rather than something that just some extension of the earth. All right, so we'll just pause here for now. It's 7:02, so we'll start at 7:07. All right, so let's get started. Okay, so we talked about the origin of the Earth's atmosphere, and hopefully you have an understanding of why the Earth's atmosphere is the way it is now. And okay, now let's talk about the interior of the Earth. So it's not easy for us to drill into the Earth to find out what's inside the Earth, right? You might think that, okay, maybe we can just drill into the Earth and just keep going in deeper and deeper into the Earth to find out what's there. But actually, that's not easy to do at all, because things get really, really dense as you go deeper and deeper. And so we cannot drill for beyond a depth of maybe 20 kilometers. That's about the deepest that anybody has been able to drill. You cannot drill any deeper than that because the rocks are so dense that we don't have any equipment that will be able to drill into them. So 20 kilometers is about the deepest we've been able to drill. And what is the radius of the Earth? Do any of you remember? What is the radius of the Earth? It's 6,400 kilometers is the radius of the Earth. So 20 kilometers, we have not even scratched the surface of the Earth, right? So there is a lot that, I mean, it's just impossible for us to drill down any deeper than that. So how can we possibly know what's inside the Earth? So we can only use indirect techniques in order to find out what's inside the Earth. So um, the most important of these indirect techniques to find out what's inside the Earth is seismic waves. So what are seismic waves? So whenever we have earthquakes, earthquakes are major disturbances um, just underneath the Earth's surface. So whenever these disturbances happen, you have vibrations which spread out in every direction um, as a result of that disturbance. So let me just very briefly explain why you have these disturbances. So later on in this chapter, we are going to talk about how the Earth, so this is the Earth, and this is the crust of the Earth. The crust is the outermost layer of the Earth, which has which contains the oceans and the continents. So that is the crust, right? So the crust of the Earth, basically, the crust and the upper part of the mantle. So this part is called the crust, and this whole region, and this is called the core of the Earth. So we've seen this diagram in the last class, and this portion is called the mantle of the Earth. Mantle. So the crust and the upper part of the mantle, the topmost part of the mantle, uh, form a solid shell because it's hard. So the crust and the uppermost part of the mantle, this region that I'm shading, is really hard. And it's like the shell of an egg. So it's basically, it forms an outer shell for our planet, right? So what's underneath that is a layer of soft rock right underneath that hard shell. So this region, which I'll just shade with a different color, is a region of soft rock, soft, runny type of rock, which has the consistency of pudding. It's not liquid, but it's so basically what happens is the hard outer shell of the Earth can move around, right? And not only that, the hard outer shell of the rock is not like a one continuous it's not continuous, it's broken into pieces, and these pieces are called tectonic plates. So didn't mean to erase that. So it's not completely rigid. It's broken into pieces. So there might be a gap over here. There might be a gap over here. There might be a gap over here. So the hard outer shell of the Earth is broken into these pieces. And these pieces, each such piece is called a tectonic plate, right? And these tectonic plates move around all the time. So this is all covered in a lot of detail later on. So I will talk about this. I do talk about this in a lot of detail later on in the chapter. So I'll just show that to you over here. So yeah, so you can see the hard outer layer of the Earth right here, and you can see how it's cracked. It's like having an egg with its shell, with cracks on its shell. So each of these segments that the hard outer shell is broken up into are called tectonic plates. And you can clearly see the tectonic plates in this picture. And so these tectonic plates, since they're sitting on a layer of soft rock, softer, mushier rock, they can move around, right? And so as a result of moving around, they can often bump into each other, right? They can bump into each other, they can move away from each other, or they can sort of grind past each other like this. So they can grind past each other like this. So these are the different things they can do. They can bump into each other, they can move away from each other, or they can sort of grind past each other. So this is what you'll study at the end of this chapter. And so this process is called plate tectonics, and it has lots of fascinating consequences. But one of those consequences is an earthquake, because when these two tectonic plates are grinding against each other, they are both uneven surfaces. So if you rub two uneven surfaces against each other, so that's going to be a rough and bumpy ride, right? And so when these two tectonic plates are sort of grinding against each other, you're going to have you'll often have these large disturbances and like these large jolts, and that is what causes earthquakes. So the reason that I'm telling you this now, even though it's covered later on, is because I want to show you this really nice video that somebody made explaining why you have earthquakes, and I want you to watch this video. So let me optimize for video clip, and let me show you this video. So what causes earthquakes?
Science, we've discovered what's inside the Earth. So what is inside the Earth? Well, when I look at my model,
Can you guys hear the sound properly?
Yes.
Okay.
Yeah.
All right.
I see continents and ocean, but what you can't see is underneath the continents and ocean is a crust that covers the whole Earth. And underneath the crust is a warmer layer called the mantle. And then underneath the mantle is this hot inner core right at the center. So let's take a closer look inside the Earth. Underneath all the continents and the ocean, there's the crust. And it's important to remember that the crust is actually broken into pieces or plates. It's not just one. There's many pieces or plates. Through science, we've
So that's what I was telling you, that the crust is broken into many pieces and plates, and they're called plates. Each of those pieces is called plates.
discovered that all those pieces and plates actually move. Now, in another video, we talked about why those plates move. Today, we want to talk about what happens when those plates move. So we're going to zoom in and take a closer look so you can see what happens when those plates move. But to do that, to show you that, we're going to use spray cheese to actually be the mantle right under the crust. And then we're going to use graham crackers to be the crust. So first we need to lay down the mantle, the part right under the crust. And to do that, I'm just going to spray some of this cheese. It's important to remember that this mantle is hot and parts of the mantle are moving. And then we have the crust. The crust sits on top of the mantle in pieces or plates. And because parts of the mantle are moving, that means parts of my crust are moving, and that's what we want to look at. Remember that continents and oceans are sitting on top of this crust, and those plates are moving, and one way those plates can move is those plates can actually move apart. When they move apart, that mantle actually forms new crust, and when the plates move apart, this is happening under the ocean. Actually, new crust is added as those plates move apart. And right here, as the plates move apart, the mantle cools down and it forms new crust. So we've seen that plates can actually move apart, but let's take a closer look at what happens when plates slide past each other. Okay, so we've zoomed in so we can take a closer look at what happens when the plates slide past each other. Watch what happens as I slide the plates past each other. It's important to remember it's not a smooth ride. It's actually quite bumpy. In fact, that bumpy ride as plates slide past each other, that's what creates earthquakes. So we've talked about what happens when plates move apart.
Yeah, so you should definitely watch the rest of the video where he talks about the other consequences of plates, of what happens, of how the plates interact. That's going to be helpful at the end of the chapter when we talk about tectonic plates. But you can hopefully understand what causes earthquakes. So it's when two plates are sort of grinding past one another that it's this bumpy ride when the two plates are grinding past one another, and that's what often causes these sharp jolts, which are what we perceive as earthquakes. All right. So these vibrations, so whenever you have these jolts that happen, these vibrations spread out as waves, and these waves are called seismic waves. And these waves carry a lot of information about so these waves are very, very useful for us to analyze because they help us understand the inside of the Earth. I'll tell you in a minute how. So there is a device called a seismograph, which can pick up these earthquake waves, right? All right, now there are two types of seismic waves. They are the P waves. They're called P waves because they're waves of pressure. The name is not that important. And I mean, the pressure waves name is not that important. And the other type of wave is called the S wave. So I want you to remember these two names, P waves and S waves. So the P waves are waves that travel more or less like this. So you have the wave going from left to right, and it's sort of, you have alternate compressions and expansions. I'll show you an example of that in just a second. And these waves move at a speed of 5 to 6 kilometers per second. So 5 to 6 kilometers per second would mean around 10 to 12,000 miles per hour. So pretty fast by our standards. And they can travel, the most important property is this one, they can travel through liquids and solids. So they can travel through everything, liquids and solids, right? And so since they travel faster, they're always the first ones picked up by a detector when an earthquake happens. Kaylee, I'll get to your question in 1 second. And the other type of wave is called an S wave. So these S waves sort of wave side to side as the wave moves along. So if the wave is going from left to right, the S waves will sort of sway side to side. And I'll show you an example just a second. They move a little bit slower, 3 to 4 kilometers per second. Very important, they cannot travel through liquid. So the S waves can only travel through solids. They cannot travel through liquids, whereas P waves can travel through liquids and solids. So they can travel through anything. And since the S waves are a little bit slower than the P waves, they arrive a little later. So using a slinky, it's possible to show both S waves and P waves on a slinky. So I'll show that to you. And then we'll get to Kaylee's question. So here is a stretch slinky, and I'll first show you the equivalent of S waves. So this is an example of an S wave traveling through the slinky, right? So this kind of wave is an S wave. So they're showing it, oops. So this is an S wave. Okay, and what about a P wave? A P wave looks like this. And if you're not able to see the YouTube videos very well right now, you can always click on the link on your own computer and you can see it later. So if you shake the slinky side to side, the waves that you get now, these waves are the equivalent of S waves. So the S waves sway side to side and the P waves sort of sway front and back. So these are S waves that you're seeing on the slinky right now. All right, yeah. So Kaylee, what's your question?
Sorry, this is just kind of off topic, but
Sure, yeah.
what does seismology and like the earthquake and stuff, geography, I mean, have to do with like astronomy?
Yes, that's actually a very good question. So unless we understand our own planet, we will not be able to understand other planets, because so a lot of the things that we are learning right now is going to be very, very useful in understanding other planets. So today we learned about the greenhouse gases and the greenhouse effect and what carbon dioxide, how carbon dioxide regulates the temperature. So now that you understand this, now you will be in a position to understand why Mars is so insanely Venus is so insanely hot. So there's something called a runaway greenhouse effect going on Venus. And but unless you know what the greenhouse effect is, you will not be able to understand the runaway greenhouse effect on Venus, and also why Mars is so cold. So unless you understand the role played by carbon dioxide, you will not be able to understand that. That makes sense?
Yeah, yeah,
Yeah.
totally. Thank you.
Yeah, and also, so there are two reasons why this chapter is very important. One is that it's just fascinating. I mean, it's our planet. It's just so fascinating. Second is a lot of the things that we learn in this chapters applies directly to the other planets. Right? All right. So, okay. So we learned about the P waves and the S waves, right? And right. Any questions about that? Is that clear to all of you? Okay. Now how is it that these S waves and P waves are useful in understanding the structure of our planet? So how do they help us understand the inside of our planet? I'll give you one example of that. Suppose you have an earthquake right here. Suppose an earthquake is happening right here. So immediately, so this picture is basically a picture of the Earth with one part sort of cut out so you can see what's happening inside. So an earthquake happened at the right side over here, right? So what that's going to do is that it's going to send out P waves and S waves in every direction. So if you have a station over here, the station here is going to pick up both P waves and S waves, right? Because both of them will get there. The the P waves and S waves are both traveling through solid rock, so they'll both get there. Station over here will also pick up P waves and S waves. However, all the stations in this region, in this whole region, all the stations will not pick up any S waves. So you can see it says here, no S waves. So none of these stations over here, like this station, this station, this station, if you have station, there are seismology stations all over the world. Every city has seismology stations. So none of these stations will pick up any S waves. They will only pick up P waves. What does that tell us? Can you guess why these stations on the left side will not pick up any S waves? What does that tell us? What kind of material are S waves not able to travel through?
Okay, Google. What kind of material are S waves not able to travel through?
I don't think Google
Water.
will be able to answer that, but yeah, you can try. Anyway, we just talked about that. So what kind of material will can S waves not travel through? It's on this slide. So can you tell me what the answer is?
Not travel through liquid, through water.
Yes, through liquid, not just water, any kind of liquid. So what this tells us is that part of the core of the Earth must be liquid, because the S waves are not able to get through from one side of the Earth to the other side. The P waves are able to get through it. That makes sense? So part of the Earth must be liquid, and this we can reach this amazing conclusion by just studying the pattern of waves coming out of earthquakes. So just to repeat this, so we had an earthquake. So this is the Earth. We had an earthquake somewhere over here, and S waves. The earthquake puts out both S waves and P waves, right? And stations over here, here, and here, or over here, here. These are just examples. These places can pick up both S and P waves. But if you consider a station over here, it's not going to be able to pick up S waves. It will only pick up P waves. So this is S, P, and S for all of these stations, but only P and no S. So what does that tell us? That tells us that the interior of the Earth must be liquid, because we know that S waves cannot travel through liquid. So using seismology is the study of these seismic waves, we can learn the interior, the internal composition of our planet. Yeah, Kaylee, what question did you have?
And well, if S waves can't travel through liquid, can like if you're like on a lake, like can they go through a lake?
No,
Because
they
it's
cannot
so
travel through any liquid or any water. So
really
so if the S waves are, so if you have S waves over here, so suppose you've got an earthquake happening over here, and there's a deep ocean or something. So the S waves that are starting from here will not be able to get through the water of the ocean. S
so if
waves
you're
cannot
like
travel
on
through
a
any
boat,
liquid. Sorry,
like
what's
if
that?
you're on a boat, if you're on a boat
Yeah.
on like any sort of water, you won't feel it.
you won't feel. So normally what happens is that earthquakes you won't feel on the ocean unless you have a tsunami. So the earthquake might shake the, so if this is the ocean, right, and you're in a boat over here, the earthquake might shake the landmass, and that might send some waves through the ocean or through the lake. So you might see some large waves on the lake, but
Yeah.
you won't you won't directly pick up the S waves or the P waves.
That's pretty cool.
Yeah, and but you do have earthquakes which might happen just underneath an ocean. So you might have an earthquake which happens somewhere. This is, let's say this is the basin of the Pacific Ocean, and you might have an earthquake somewhere over here, and so that is going to tremendously shake the land over here, right? And since the land is being shaken, that will shake the water as well. And so you might have these huge waves which are produced in the water. Do you know what those waves are called? Huge, gigantic waves. So they're called tsunamis. So you might have these huge waves which will move towards the shore and then crash into the shore and cause a lot of destruction. So that happens when you have an earthquake underneath the ocean. That makes sense? All right. So what we just learned from this, and that's what this picture is showing us, that S waves cannot, we know that they cannot travel through liquid. So the fact that we are picking up S waves, we are not able to pick up S waves on 2 points which are directly opposite on the Earth, it tells us that the interior of the Earth must be liquid. Since only P waves can go through. And so we have a lot of data, like we've been studying earthquakes for like 150, 200 years. And so we have tons and tons of data, and earthquakes happen all the time, all over our planet. And so we, having studied all this data, and noticing that when the earthquake happens on one side of the Earth and the other side of the Earth never picks up S waves, it only picks up the P waves, it tells us that a large part of the core must be liquid. There's also more evidence which seems to indicate that the inner part of the core is solid. So it seems that the core of the Earth is divided into 2 parts. So there is a liquid outer core, and inside you've got a solid inner core. So this inner core is solid. How do we know that there's a solid inner core? That is based on how the P waves seem to bounce off the solid inner core. The P waves can travel through the liquid core because they can travel through anything, but they seem to change direction in a particular way. And so that seems to be caused by a hard inner core, which sort of makes these waves bounce off. And so studying these seismic waves allows us to understand the inner interior structure of our planet. Okay, all right. So basically from here, what we can learn is that the radius of the core is around 3,500 kilometers, and the solid inner core has a radius of 1,300 kilometers. Okay, so using a lot of data, mostly seismic data, geologists can understand what the composition of the Earth is. So we know that the mantle of the Earth, so here's the diagram that you've been seeing since the beginning of this chapter. So the thin outermost layer is called the crust, right? It's a very, very thin outermost layer on which the oceans and the continents sit. That's called the crust of the Earth. And then the inner part is just underneath that is the mantle of the Earth. And then you have the outer core, which is liquid, and the inner core, which is solid. So that's the structure of our planet, right? Um, we find that the density and the temperature both increase as you go deeper into the planet. So the material gets denser and denser, and the temperature also increases. It gets hotter and hotter and hotter. Let's look at the density. So we find that the density at the surface of the Earth is the density of rocks. And we've seen in chapter 6 and the early part of chapter 7, the density of rock is around 2,000 to 3,000 kgs per meter cubed. And so that's the density at the surface. That's on the left part of our graph. Then as you go deeper into the Earth, the density keeps on increasing. So the density in the mantle keeps on increasing until it goes up to around 5,000 kgs per meter cubed. So that's very, very dense rock. And then you get to the core of the Earth, right? And there the density suddenly jumps up to 10,000 kgs per meter cubed. So extremely, extremely dense, and ultimately goes up as high as 13,000 kgs per meters cubed. at the center of the Earth, right? So that is how the density fluctuates, and we've learned this from studying seismic data. So the density increases as you go deeper into the Earth, and then when you get to the core, the density just suddenly jumps up to 10,000 kgs per meter cubed and goes up to a maximum of 13,000 kgs per meter cubed. And what about temperature? The temperature, if you take the temperature to be in kelvins, the temperature at the atmosphere is just room temperature, which is around 20 kelvins or so. But then as you go deeper into the Earth, the temperature keeps on increasing, but it doesn't increase abruptly. It just keeps on increasing, increasing, increasing until you get to the center of the Earth right here, where the temperature is extremely, extremely high, like about 5,000 kelvins. What is the temperature of the surface of the sun? Does anybody remember from chapter 4? The temperature of the surface of the sun is 5,800 kelvins. So you can see that the temperature at the center of the Earth, at the center of the Earth's core, is almost the temperature at the surface of the sun. It's 5,000 kelvins. It's extremely, extremely hot at the center of the Earth. Okay, so now why does the density of the Earth fluctuate in this weird way? Like, why does it increase, and then suddenly jump up? And then, so that is because scientists believe that the material changes. So the mantle is entirely made up of rock, but the core is made up of iron, which is a different type of material. So it seems that the Earth is very neatly differentiated. So you have, at the center, you have the heaviest stuff. You have iron at the center. And then as you go further out, you have denser rocks, then less dense rocks, all the way until you get to the surface, where you have the lightest rocks, which have a density of 2,000 to 3,000 kgs per meter cubed. So this is called differentiation of the planet. Differentiation means that the heaviest stuff is at the center, and as you go further outwards, you have lighter and lighter stuff. So the Earth is very neatly differentiated. All the heavy stuff, the iron, so the core is made up of metals, iron and nickel. These are metals. So all the heavy stuff, all the iron is present in the core, and then as you go outwards from the core, you have lighter and lighter rocks, and you have the lightest rocks on the surface of the Earth. All right. Okay, so that's the interior of the Earth. Now, let's talk a little bit about the mantle. So we've not been able to drill down into the mantle yet, because it's just, we haven't even been able to drill more than 20 kilometers. So how do we learn about the mantle? One way we can learn about the mantle is because volcanoes can provide us samples from the mantle. So what is a volcano? A volcano is when you have molten rock underneath the surface of the Earth, and that molten rock is under a tremendous amount of pressure. Sometimes with enough pressure, it might just find its way to the surface of the Earth. It might just blast its way to the surface of the Earth. And so you have this molten rock coming out of the surface of the Earth, and that is a volcano. So volcanoes provide us samples of rock from the metal, because they are basically rocks, molten rocks from the metal, from the mantle, which have come to the surface. So by studying those rocks, we can get an idea of what kind of rocks are there in the mantle of the Earth. So the upper mantle seems to be similar to the iron magnesium silicate mixtures known as basalt. So remember that there are two types of rock on the Earth. So there are two types of rocks. So one of them is basalt, and the other one is granite. So the crust of the Earth is mostly made up of granite. So most of the rocks that you see around you, like if you just go outside and pick up a stone, uh, that's most likely granite. But the type of rocks that you see around volcanoes, like if you've ever visited a volcanic region, you'll see these really dark black colored rocks over there. So that is basalt. So basalt has a higher density, 3 to 3,000 kgs per meter cubed, whereas most of the rocks that make up the crust of the Earth have a much lower density, which is 2,700 to 3,000 kgs per meter cubed. So it seems that the upper mantle is made up of this dense basaltic rock, Whereas the crust of the Earth is mostly made up of this lighter type of rock called granite, right? And you know that dense materials will sink down and less dense materials will float up. And so that explains why the upper crust is mostly made up of granite, and the mantle is made up of basalt. All right. Okay, so let's do this one question. Since there's only 3 of you, maybe you can just type your answers in the chat. So which of the following do you think is the densest part of the Earth? All right, no one? Okay, so the densest part of the Earth is the core. Yes, that's the correct answer. The densest part of the Earth is the core. Okay, all right. So I just talked about differentiation. So what does differentiation mean? Differentiation is the variation in the density and composition of a planet, right? Um, and in the case of the Earth, we find that the Earth is very nicely differentiated, which means very neatly differentiated, which means that the densest stuff is at the core of the Earth, and then as you go further out, you get less and less dense stuff. So the one question is, why is the Earth so neatly differentiated? Why is the Earth differentiated like this? Like, why is the densest stuff at the center and then lighter stuff as you go further out? The answer is because most of the Earth was once completely molten. It's hard for us to imagine now, but most of the Earth was once completely molten. Why was it molten? Because the Earth was constantly being bombarded by these by asteroids and other rocks and stuff like that. And so the early history of the solar system was very violent. So there was always stuff slamming into the Earth. And so these collisions created enormous amounts of heat, and that heat was sufficient to melt the entire planet. So there was once a time when our planet was just almost completely liquid, it was not solid at all. So and so when you have liquids, uh, you know that heavier liquids will always sink to the bottom, right? So if you just put some thick honey or nectar in water, you'll find that the thick honey will immediately settle to the bottom and the water will rise above that. And so when the Earth was molten, gravity pulled all the high density stuff like the metals towards the center of the Earth. And so the high density matter sunk to the core, and the lower density matter floated up, right? Floated up. And as a result of that, that's why the Earth is so neatly differentiated. You have at the center, you've got all the high density stuff. And as you go further out, you have less and less dense stuff. Okay. Now, a remnant of this molten phase is that the central temperature of the Earth is very close to the sun. And we've seen that the temperature of the Earth at its center is extremely hot. It's 5,000 kelvins, which is almost near the temperature of the sun. All right. Now, the next thing that we're going to talk about is planetary heating. So we'll try to understand why planets get hot and also how planets get cold, get cooler. And so this will help us in understanding other planets later on. All right. So, and also it will help us understand the history, the thermal history of our planet. So how do planets get hot? So planets can the interiors of planets can get hot for 3 reasons. The first is the heat is called the heat of accretion. And we've already talked about this. We've talked about how the very early in the history of the Earth, objects would always be colliding. So in the history of the solar system, there would be lots of collisions happening. So objects would always be slamming into the very young Earth, right? So when objects keep on colliding with the planet, each of these collisions involves a lot of energy, and so a lot of energy gets converted into heat. And so that would heat up the planet. So if a planet is constantly being bombarded with stuff from every direction all the time, all of these collisions will transfer heat energy to the planet and will heat up the planet. So this is called heat of accretion. So this is one way in which planets can get hot. The second way in which planets can get hot is called heat of differentiation. So what does that mean? We've just seen that when a planet is molten, then heavy material sinks to the bottom and lighter material sort of rises to the top, right? When a planet is molten. So that process where the heavy material is sinking to the bottom and lighter material is rising to the top, that involves some friction, right? Because the heavy stuff is sinking down, the lighter stuff is rising up. So that friction generates some heat as well. So that is called heat of differentiation, because differentiation is that process where you have that separation. The heavy stuff goes to the bottom, light stuff, or to the center in the case of a planet, light stuff comes out. So this is called the heat of differentiation. As different materials of different densities are sort of moving to their respective places, there's a lot of friction between them, and that generates heat. The third and one of the more important ways of planetary heating is called heat of radioactivity. What is that? So we're going to talk about radioactivity probably in the next class. It's in the videos that I uploaded. So radioactivity can generate heat. So what is radioactivity? Radioactivity means that there are certain elements, like very heavy elements like uranium, potassium, thorium. So these elements are unstable. So if you have a uranium nucleus here, for instance, it's unstable. It's not going to last for very long. It will keep on shooting off these particles, which are called alpha particles. And that is what radioactivity is. So this heavy nucleus will keep on, or a collection of heavy nuclei will keep on shooting out particles. And so these particles are shooting out of that nucleus. And so they will bounce into, they will hit whatever is nearby. And so every time they hit something, they're going to generate heat. And so as a result of, if you just keep a radioactive material inside a box, after a while, you'll find that that temperature of the box is increasing. And that is because the radioactive material is constantly shooting stuff out, and that the stuff, when it collides with things, it just generates heat. So that is called heat of radioactivity. It heats very, very slowly, but if you have millions of years to wait, a lot of heat can accumulate. So when radioactive nuclei decay, subatomic particles fly off at high speeds, as I just said, and collide with neighboring atoms and heat them up. So that is the heat of radioactivity. So these are the three ways in which interiors of planets can get heated, right? And here is a picture which explains this. So accretion is the heating through collisions. Something slams into the earth, and the impact, the energy of the impact is converted into heat energy. Differentiation is when light materials rise to the surface. So here you can see this arrow. If you follow this arrow, you have some blob of light material rising up and heavy material sinking down. So so here's some heavy material sinking down. So this friction between light material rising up and heavy material sinking down is what generates is the heat of differentiation. And the heat of radioactive decay is when you have these radioactive materials. So these star kind of things they've drawn over here are radioactive materials. So if you just have radioactive materials sitting inside some rock, that rock is guaranteed to get hot after a while. It will take a very long time though, millions of years, but it will get very hot. So these are the three ways in which planets can heat. How do planets cool down? So planets can cool off in the following ways. So the first method in which a planet can cool is through convection. So we talked about convection in the last class. I told you that uh, if you have this, I showed you this demonstration where if you have some water and if you heat water in a pot, and if you heat up the water, then what's going to happen is that the hot water will rise up, right? And cold water is going to sink down and take its place. And so you might have hot water rising up like this and cold water sinking down and taking its place. So these are called convection cells, right? Where the hot water is rising up and the cold water comes down. And this will serve to heat up the entire pot of water. However, what happens to the hot water when it rises to the surface? So when it rises to the surface, it sort of transfers the heat from the bottom of the pot to the top, right? And so the heat has a chance to escape. And so convection is one way in which cooling happens. So the hot stuff rises up and goes to the top, and that gives a chance for the heat to escape. So convection is a method of cooling. Um, so in a planet, if the interior of the planet is extremely hot, so if let's say that the core of the planet is extremely hot, then some material, some molten rock from near the core can rise to the surface, and some other rock might sink down, but the hot molten rock that rose to the surface might has a chance to lose heat, and so that way the planet can cool down. So that is convection. The second method is called conduction. Conduction is the direct transfer of heat. So if you just hold, conduction is something that you're very familiar with. So if you have a like a piece of like an iron rod, for example, and if you hold that inside in a fire, that's my fire. Okay, so if you hold that inside of in a fire, after a while it'll be really hard to hold on to the other end of the rod, right? So suppose this end of the rod is held inside a flame and it's a metal rod. At first you might be able to hold on to the other end of the rod, but after a while you'll find that the other end of the rod has gotten very hot, and you'll have to put on some gloves or mittens in order to hold on to it. And that is because the heat has conducted directly through the rod. And so that is called conduction. So that's another method in which a planet can cool down. So the heat in the core of the planet might conduct directly through the rocks and leave the planet. So that is called conduction. And conduction is not very efficient in transferring heat because rocks are usually not good conductors of heat. Metals are very good conductors of heat, but rocks are not good conductors of heat. The final method of planetary cooling is radiation. So you know that when you have a very hot object, it starts, and if you leave it for a while, it will eventually get cold. So suppose you put a burrito inside the microwave. You're going to eat it for dinner now. Put it inside the microwave, and let's say that you instead of cooking it for 2 minutes, you accidentally cook it for 5 minutes. So when you take it out of the microwave, it's going to be extremely hot, right? And so what do you do at that point? So what you're going to do is you're just going to let it sit on the counter for a little bit, right? So for a good 6 minutes or so. If you just let it sit on the counter, you'll find that it's cooled down. How did it cool down? It cooled down because when it's at a high temperature, it was radiating infrared radiation, right? It was giving off more infrared radiation. And so as it gives off more and more infrared radiation, it loses its heat, right? And that is how it cools down. It cools down by giving off infrared radiation. And so radiation is the third method in which a planet can cool. It's the loss of heat to space through just by just giving off infrared radiation. So these are the three ways in which planets can cool. And we are going to talk about planetary heating and cooling in the next few chapters. Okay, so here is a nice diagram. So convection is when you have stuff rising up, hot material rising up, cooler material sinking down. Let's see if I can change the color. So you have hot stuff rising up, cool stuff sinking down. And so when the hot stuff rises to the surface, it has an opportunity to cool down. And conduction is the direct transfer of heat. So you have some hot material over here, and the heat just directly transfers and gets to the surface. And radiation is when you have heat on the surface. You have a hot surface, and it just gives off infrared radiation and cools down. So that's the third method is radiation. So these are the three main cooling processes in planets. Okay. All right. Any questions about the heating processes and cooling processes?
No.
Okay. All right. So the last thing that we're going to cover today is the thermal history of our planet. So the Earth formed 4.5 billion years ago. 4.6 billion years ago was when the Earth formed. And we've discussed this in chapter 6. The way it formed was by capturing material from its surroundings, right? It turns out that there were two distinct thermal phases. Thermal phases means if you divide the history, if you look at the history of the Earth in terms of the heating or cooling that's going on, so you can break it up into two phases. So there was an early heating phase which lasted for around 50 million years, and then a slow cooling phase which lasted for 4.5 billion years. So the early heating phase was when the Earth was just constantly being bombarded by stuff. So like this picture shows, you have this constant non-stop bombardment all the time from every direction. So that created tremendous amount of heat in the planet, and the entire planet was molten, right? Um, so the planet was very, very hot. But then what happened was that the Earth more or less cleared out its neighborhood. So there was not much stuff left to collide with the Earth, right? So the Earth had more or less cleared out its neighborhood. And so from that point on, it just started cooling, right? And so it's been cooling very, very slowly. And the Earth cooled from outside in. So the outermost part of the planet cooled and solidified, and then it started cooling as then more and more of the planet started cooling and solidifying. Uh, However, the cooling process was not very fast, and that is because of radioactivity. So since a lot of rocks have radioactive materials inside them, we've just discussed how when you have radioactive materials embedded inside the rock, the radioactive materials constantly generate heat of their own, right? And so it makes it very difficult for the rocks to cool down. So that is why the Earth has been cooling so slowly. And the interior of the Earth is still extremely, extremely hot. Because a lot of the heat has not left, it has not had an opportunity to leave, just because rocks are a very bad conductor of heat. And more importantly, the interior of the Earth is extremely hot and molten because of the presence of radioactive materials. So that is why the interior of the Earth is still molten, and we have a liquid core. That makes sense? So it's because of the presence of these radioactive materials inside the rocks that there's constantly heat being generated. And since rocks are bad conductors of heat, the heat cannot conduct outside very easily, and so the heat just remains trapped and keeps getting hot, and it keeps getting hotter and hotter and hotter because of the radioactivity, which is constantly generating heat. And as a result of that, the inside of our planet is very, very hot. That makes sense? So the Earth has been cooling, but very slowly. Why has it been cooling slowly? Because of the presence of radioactive materials inside inside the Earth. Is that completely clear? Does that make sense?
Yes.
Thank you.
All right. Okay. Bye.
Thank you.